more abstract example we had before, this Fx space, the vector space of polynomials with real coefficients and with real variable x. So by real I mean from the set of real numbers. And then we had before that one vector, it's actually a polynomial if it's identically zero polynomial that would play the role of the zero vector in this vector space of polynomials. Also, for example, if you consider another vector like v1 vector, which is actually a function of x, a polynomial, which is identically 1, constant 1 polynomial, that's also in the vector space. Or for example, v2, let's say that this is the x function and this is a polynomial. Or v3 vector, let's say that this is the polynomial v3x, that's actually the x square polynomial. So please note the difference that we cannot really plot the vector space f of x like before. What we can do is in the xy coordinate system we can plot single vectors. So when you talk about the constant 1 vector, that's actually constant 1 function. Or the x is actually the v2 vector, it's actually a function. And for example, v3 is a quadratic function, that's a polynomial. This is really a function space, f. And then, for example, we could look at the span of v1 and v2. So that means a1, v1 plus a2, v2 linear combination, or possible linear combinations where a1, a2 go through all the real numbers. Writing in how this looks, v1 is 1, so a1 times v1 is just a1. And v2 is the x function, so you get a2x, where a1, a2 are real numbers. And then if you look at this a1 plus a2x, where a1 and a2 are numbers, we usually use a different notation for this that should make it easy to identify this. If you denote a2 with m, and first you write it down as mx, and then the other constant b, so here m and b are real numbers, then this span of v1 and v2, it's actually a subspace of f of x, the polynomials. So these are special polynomials. These are linear functions or linear polynomials. All the linear functions should be written in this way, mx plus b. Well, there are other forms of linear functions, but this is one form with the slope-intercept form. Also, please remember, actually we had the notation p1x before for the degree 1 or less polynomials. For example, if you look at 3x plus 5, that's one element of p1x, and that's a vector because it's a polynomial and it has degree 1 or less. So and this is in the span of 1x polynomials. If we think about the span of 1x, x squared, and so on, dot, 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 if we don't have an n to this list, then this means an infinite list. So if you think about this, these are linear combinations of arbitrary powers of x. So any power of x can happen here, it can come up here with any combination of multipliers. So actually this gives you the whole space. We will talk about it later, maybe in the future, but this is an infinite list already, and we don't work much with infinite lists. Another example, this is a typical notation, L01, integrable functions over the open interval 0, 1. It's actually, in this case, it might be important that it's open interval. So this is with words, and then with set notation. So this is about function. It's a function space. We simply denote in general functions with f of x. And then the property of this function, so we separate this specification with this vertical line, that they are integrable. That means that when you integrate from 0 to 1, and we usually use the absolute value notation for this integrability, because if you integrate positive or negative, you can get cancellation. So the integral of the absolute value from 0 to 1 is less than infinity. So this is the set of all functions that have finite integral. In fact, this is a space of all functions that have absolute value integral that is finite on the interval 0, 1. So let me mention why this is actually a vector space. Again, we have the three properties. Maybe I use now the I notation for the items. The first one is that this is not empty. It's not equal to an empty set, so we have to show that at least one element is there. I'm going to have several examples, but right now let me choose f of x equals identically 1 for x in the interval 0, 1. So if you integrate this function 0, 1 absolute value f of x dx, you integrate 1 and you get 1 as an integral. And this is finite, and because that's the property of these integrals, the integral is supposed to be finite. All the functions with this property are in the set. That means this function 1 is in the set because it has a finite integral. So that means this f of x identically 1 is in that vector space 0, 1, the integrable functions. The second property is that the plus stays in the set when you add together two functions. So it says that if f, g are in this space, then f plus g should be in this space. Now, if f and g are in this space, that means their integral, absolute value integral, is finite. It can be different numbers, but the property just says that it's a finite integral. So this is the property of the set. Then if you add together the functions, we also have to check that it's in the set, so we have to check what this integral is. The integral from 0 to 1, f plus g of x is the new function, the sum function with absolute value. But then the way we evaluate a sum function is that we add them together at every x. So this is f of x plus g of x, absolute value. We're supposed to show that this is finite, less than infinity. Now, a basic inequality for absolute values is that you can have some cancellation, so this doesn't equal to the sum of separate integrals. What we know is that if you separate this into separate terms, then you get maybe a larger one. So if you write f of x absolute value plus g of x absolute value, this might be actually larger sums. Since inside the absolute value you might have some cancellation. Like if you have minus 2 plus 2, you can get a cancellation, get 0. But you get a larger one if you take separately the absolute values, you get plus 2 and plus 2. So this is a basic inequality for absolute values. And then we have that the basic property of the integral is that you can integrate term by term. So you get the absolute value of f of x integrated from 0 to 1 plus from 0 to 1 the integral of absolute value g of x. And then for this already we know that both of these are finite. And then we know that if you have two finite numbers, the sum is also finite, less than infinity. Strictly less than infinity, that means finite. So what we get is that the sum has finite integral. That means the sum, by definition of the set, if it has finite integral with absolute value, then it's in the set. So that means f plus g is also in L01, which means that the addition doesn't go out from this set. It stays inside the set. It's closed to addition. The third property is that if you have a scalar C from the scalar field and f from this vector space or set as 0, 1, we need that C times f, the scalar multiple of a vector, is also in that set, which means the scalar multiplication also stays inside the set. So again, we do the same thing. We use the basic property of that set that says that the integral from 0 to 1 absolute value must be finite. Then we check this CF function. Well, the CF function is supposed to be evaluated as C times f of x for all x. And then we have to take the absolute value integral of that. And then somehow we have to use this property. What we want to do is factor out C somehow. Well, first of all, you can factor out absolute value C, not just from this absolute value part, but also from the integral. And we get C, absolute value C times the integral from 0 to 1 of absolute value of f of x dx. And then since this is finite, scalar is supposed to be also finite, so a finite scalar times a finite number, that's also finite. Finite number times finite number is finite. So the fact that the C times f has finite integral over 0 to 1 with absolute value means that CF stays inside the vector space L0, 1. Well, first of all, it's a set, but then using these properties 1, 2, 3, what we obtain is that L0, 1 is a vector space. Well, strictly speaking, it's supposed to say that this is a subspace in the vector space of all functions. But we know that the subspace is also a vector space. Now from calculus 2, if you think about this, you should know that all polynomials have finite integrals on the interval 0, 1. So that means that the vector space of polynomials is actually a subspace of L0, 1. So we have function spaces now. If you look at the function, for example, f of x equals 1 over x. If you want to check whether it's in L0, 1 or not, then you have to check this basic property, the integral from 0 to 1, 1 over x, absolute value dx. Well, from 0 to 1, x is positive, so that means we don't need the absolute value sign, just 1 over x dx. Let me remind you from calculus 2 that this is actually an improper integral because the function is undefined at 0. So the way we're supposed to get over this problem is that we integrate from epsilon to 1 and then we push this epsilon to 0 from the right through positive epsilons. And then 1 over x is defined from epsilon to 1. That means that this is the limit as epsilon approaches 0 from the right. The integral of 1 over x is natural log. So we get natural log at the upper limit 1 minus the natural log at epsilon. Logarithm of 1 is 0. So we end up with minus the natural log of epsilon when epsilon goes to 0 from the right. And if you know the shape of the logarithm function, you see that this is not finite, infinity. For this 1 over x function, we got infinite integral. That means this f of x equals 1 over x is not in this vector space. So not all functions are integrable. But then, for example, again from calculus 2, when you have g of x equals 1 over square root of x, which is x to the minus 1/2, it turns out that this is integrable. Integral from 0 to 1, x to the negative 1/2 dx. Again, it's supposed to go through with this limit calculation. The limit as epsilon goes to 0, 2 times square root of 1 minus 2 times square root of epsilon, and then the limit of the square root of epsilon as epsilon goes to 0 from the right is 0, so we end up with 2, which is finite. What we obtained is that the g of x equals 1 over square root of x is in the L01 integrable functions vector space. If you go back to the previous examples, with for example the polynomials, I mentioned that the span of 1x, x squared, and all these powers actually equals to the space of polynomials, vector space of polynomials. It's completely not obvious what would be the spanning set for these integrable functions. So next we continue with the linear independence, and finally we construct basis for the vector spaces.